So I hope all of you have understood the gear module. Okay, so in the last class we have completed that particular module. Okay, so we are going to start the next module today, which is basically about belt drive and other friction drives. So as I have already told, okay, so today we are going to start the next module. So the gear module is already over. So I hope all of you can do and solve some problems related to that. So try solving some other problems too, okay? Because due to time constraint, we cannot like in class we cannot solve too much problems, no? Okay, but the type of problems already like different types of problems already has been discussed. So that type of different problems you try, okay? Understood?
Yes, sir.
So So any confusion up to the last module? No, then we'll move ahead with the next module. Okay. So is my screen visible?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So in the last module, we have discussed basically about gear drive, where we have seen that we are using those gear drive for transmission of motion or power from one shaft to another. So apart from this gear drive, we already have like we already know there are different means of other means of power transmission from one shaft to another. Like we have got belt drive, we have rope drive, we have chain drive, and definitely also the gear drive we use. So now, in the previous case, we have seen like these gear drives are basically preferred for transmission of motion or power from one shaft to another in case where there is like the central distance between the two shafts is small. Okay, so but whenever we have to go for like central distance, large central distance. Okay, so when the central distance between the shafts is kind of large. Okay, so in that particular case, this gear drives are now it is not a kind of now it is means not they won't remain a valid solution for a longer central distance. So in that particular case, we generally use like those wheel drives, rope drive, chain drive, etc. So and this wheel drive, rope drive, or chain drive, they are kind of flexible kind of connection or flexible kind of drive that we call. But those gear drive that we have seen, it was kind of rigid drive. So here this belt, rope, uh, the sense they undergo certain deformation in their, or you can say they have got certain flexibility to undergo deformation without withstanding any kind of failure and all. Okay, that's why they are kind of flexible drive we can call it. Okay, so now in this particular module we are basically going to discuss about the belt drive, which is a type of friction drive only, and why we call this as friction drive. Basically, this belt. Similarly, rope drive also is somewhat similar to belt drive in nature. Okay, so this belt, rope, etc., they transmit the power due to friction between them and the pulleys. So, what if I hope by this time all of you have seen belt drives in working, maybe in the lathe machine or some other cases where you have seen. Basically, we have got a pulley. Okay, so over which we basically uh, have the belt. Okay, it runs about that particular pulley, and only is just like in the case of gears. Okay, only single pulley will not constitute that particular belt drive. Okay, so we generally have the two sub, one is the driver, one is the driven. Over this pulley actually we have got the belt found over it. Okay, so in that particular case the belt and the pulley. Okay, so in between the uh, belt and the pulley there is kind of friction that gets generated, and due to the friction between them only, that means the belt, this is the belt suppose, and this is the pulley, the uh, this one the shaft position, as you can see. Okay, so now because of that only they can transmit power. So now as you can see that basically due to the friction and interlocking between them, okay, so the power is being transmitted from the belt to the pulley, or ultimately in vice versa, pulley to the belt also, okay. So now if the power transmitted it exceeds the force of friction, then what will happen, the belt or the rope, it will not be able to properly transmit that particular power, and it is going to, there will be phenomenon called slip. So it's going to slip over the pulley. So what is this particular slip? Because of slip, it's something kind of, so it cannot hold to that. Suppose that a regular belt, it cannot hold on to that particular pulley surface, and it is going to slip. And during that time, our expectation is that is the, like if you, this is the suppose driver pulley, this is the suppose the driven pulley. So in that particular case, this belt is mounted over that, right? Okay, this is a kind of we generally consider to be a continuous belt. Okay, this belt is kind of wound over it. Okay, so in that particular case, what is our expectation? So it is understood like suppose from, if this is the suppose pulley. Okay, this is the pulley, this is another pulley. Pulley suppose A position. Okay. So B position. So just like in the case of your gear drive we have said. So this is the shaft position. Basically onto that particular shaft, your this pulley of suitable size that is basically mounted. Okay. Just like in the case of gear drive also we have seen the size of the gear plays a particular vital role for whenever we are talking about the velocity ratio that is we are going to obtain. So here also the similar kind of thing is some valid here also. The size of the pulley, we can play with the size of the pulley so as to get a particular velocity ratio. Okay, there is a definite relationship that is there between the size of the pulley, okay, driver and the driven pulley, and the velocity ratio that is going to be obtained. So now in that particular case, our expectation is that one, basically suppose if this is the A is the driver, B is the driven, so our expectation is like, and a particular suitable belt, okay, is been here, okay, between connecting A and B. So in that particular case our expectation is when this particular wheel, or will not be saying wheel, maybe the pulley, the proper word will be the pulley, okay, when this particular pulley A is rotating, so as this belt is round over it, okay, and along with the motion of suppose your gear A, due to the friction and interlocking between them, so it was expected that the same motion will be obtained in that particular belt. Now this belt is kind of continuous running, okay, because the pulley is rotating, and along with that the belt will run over it, okay. So now in this particular side, if we look at the driven side, then the motion will be transferred from this, now belt is already having motion, so this from this belt portion to the pulley, the motion will be obtained. Okay, and what will happen depending on the directional movement of this particular belt. Okay, and the type of belting, which is can be open belting, cross belting. We'll see later on. Okay, which configuration is open belting, which configuration called as the cross belting. So depending on that, the driven pulley is going to get motion. Now, as we are saying, if we are talking about high power transmission, which is exceeding the force of friction, then this particular belt is going to slip over the pulley. That means even though the driver wheel is pulley is rotating, it is the friction force, it is going to be exceeded due to like the power transmission is exceeding the force of friction. So the belt will slip over it, and the belt will not get the particular velocity that it should have obtained from that particular your this particular driver pulley. Okay, so now if that is being it is not getting that particular velocity, that means it is kind of a loss that is happening. Okay, so now because of that, what happens because of this particular slip, so we cannot get the exact velocity ratio from the belt drive. So that's why this belt drive, as there is uh, presence of sleep is there, and we cannot get exact velocity ratio. That's why they are not positive drives. But our gear drive, they are positive drive. Okay, so I hope that's clear. Let me know. Is it clear?
Yes, sir.
Okay. So now, just
Yes, sir.
whatever I have been saying this time, okay, I'll just in details we'll discuss. So the working of wheel drive. So as you can see, like there are two wheels. Okay, the two pulleys. One is the driving pulley, one is the driven pulley, and these two sizes you can see. Okay, this is having radius R1. This one is radius R2. Okay, and this belt of thickness T. Okay, so this is on the body. Okay, so now here what happens, this will be definitely having the driver as well as the driven shaft, that position. Okay, and onto that particular shaft only we are mounting the pulleys. Okay, so here both the shafts, that is the driver and the driven, they are provided with pulleys on them. The and these pulleys are then connected by an endless belt which is passing over this particular pulley. So this particular process is nothing but this particular belt only. Okay, so which is on for it. So there may be kind of different belt materials, like maybe it might be made of leather, rubber, balata, canvas, etc., etc. So now what happens, this belt, okay, as we were saying previously, like it has to be kind of a suitable belt that we are talking about. So actually the length of the belt, that is also important, which should be like properly calculated, and that particular belt only has to be used for a particular central distance in between two particular sizes of pulley. Okay, so now while transmitting power, the belt is basically under tension. That's why only it can actually do the transmission of motion and power. And and as like we have been saying in the previous case, okay, last like in the gear drive also you have seen. So the velocity ratio, okay, or ultimately the uh, output is obtained in the driven shaft or in the output shaft. Okay, the speed of the driven shaft, it can be varied by varying the size or ultimately the diameter of the two pulleys. Just like in the case of gears, we have seen by varying the pitch circle diameter for this particular gears also, basically it gives us a certain change in the velocity ratio. Here also it is similar. Okay, so by using pulleys of suitable size, okay, you can get a particular velocity ratio. And just like in the case of gear drive, here also, like depending on what is the suppose speed reduction or increase in speed that you want to do, so as per that proper belt as well as the belting, the size of the particular pulley you need to consider. So here, if you look at this particular figure, so this is the driving pulley. This is the uh, this is the driver pulley. Okay, this is the pen. Okay. So now this particular belt is basically on over it. Okay, and less belt is mounted over it. So this much is the it is accident. Okay, uh, uh, we are showing the thickness. Okay, like this. Okay, so this is the thickness of the belt, generally denoted by T. Okay, and these are like the uh, R1 and R2 are the two radius of this particular pulley only. Okay, and this driver, this pulley is rotating in this direction. The belt is out for it. So from this, the belt is going to get the motion like this. Okay, and continuously belt is getting motion. Now in this particular side, from the belt to the this particular pulley, the motion will be transferred. Okay, and interestingly, if you see for this particular configuration of belting, which is known as the open belt. Okay, this is the open belting configuration. Okay, so for this case, both the driver and the driven pulley, they rotate in the same direction. Okay, so now and this is continuously, this thing will happen. Okay, now uh, this is the thickness of this particular wheel. Now under while doing that particular operation, so there is basically two sides, that is tight side and slack side, which gets developed in this particular building. So now this side is something like as if it is pulling the belt towards this particular pulley, right, from this side, as if it is pulling it. So that becomes that remains under tension, hair tension, so this becomes the tight side. Now in this portion, it becomes the belt is basically leaving that particular pulley. Okay, and in this case, where this particular side of the belt become the slack side of it. Okay, and there is one like just like in the mid of that particular thickness of the belt, there is a neutral section. Okay, where there is no tension, neither compression, no neither it is neither in tension, okay, nor in compression. And effective radius is basically considered in the smaller pulley. So smaller pulley is this one. Okay, and this R2 is the your radius of this particular pulley. To that radius plus half of the thickness of the belt gives you basically the effective radius. Okay, after this much it's clear. Let me know.
Yes, sir.
Okay, So just like in the previously also we have been always discussing like in those different drives, velocity ratio is very very important. So here the velocity ratio is given by the ratio between the velocities of the driven to the driver pulley. Okay, that is n2 by n1, and in terms of your size of this diameter of this particular pulley, okay, that will be like it is in the inverse ratio, that is d1 by d2. So n2 by n1 equal to d1 by d2, where d1 and d2 are the diameter of the driver and the driven pulley. Similarly, n2 and 1 speed in rpm for that particular case. Okay. Now, as we have seen, this is only considering the diameter of the pulley. But we have seen that over that particular pulley, basically the belt is mounted, okay, and that belt has a certain thickness. Now, if we consider the belt thickness T into consideration, that small t, then the your by considering belt thickness, that your velocity ratio becomes n2 by n1 equal to d1 plus t, okay, d2 plus t. That t, that is the thickness of the material in both the side, okay, belt material gets considered. Okay. Okay, so now we are going to consider about the different types of belt. So there may be different types of belts depending on the cross section of this belt. Okay, they have flat belt, V belt, etc., etc. So now they made there a belt which is kind of a rectangular cross section. Okay, then it is a flat belt. Okay, that means if you consider the belt and cross section of the belt only, if you consider if this is kind of rectangular, this is the cross belt that we are, or a flat belt that we are talking about. Now, if this is kind of the like we have got like the trapezoidal cross section, so that is the P bill. Okay, P bill has got. So here in this particular figure, you can see this. This is the trapezoidal cross section of the belt. Okay, that is the P belt we are talking about. Okay, so now this P bill generally, as you can see, so in this particular figure, so this is one side of the scope pulley only we are showing. Okay, so generally P bill, they are uh, the in the your the pulley, basically the groove is being made, okay, and onto the groove the P bill is mounted. Okay, but in the case of your flat bill, okay, this case, okay, so here what happens, there is no this kind of groove that is being done, which is a requirement for the P-bell, because it has got this trapezoidal cross section. Okay, and because of that, actually the wedge phenomenon gets also developed, and compared to flat belt, so flat belt can P-bell can uh, transmit more power, and there is less slip in that particular figure. Those are some of the advantages. But there are like this flat bell also is are being used. So in the case of flat bell, what basically happens, the pulley is somewhat crowned. Okay, so this portion that is being made like this, open shape, so that the initially the uh, belt cross section is something like this. Okay, now if it is kind of somewhat crowned, okay, then what happens, this belt, okay, it can remain here, okay, and will get somewhat deformed, and it will be like somewhat this kind of somewhat it will get deformed and gets kind of cut kind of shape. Okay, not exactly like that, okay, but some only small deformation, and it stays on that particular pulley surface in a better manner. Okay, so that's why in case of flat bell, generally the rim of the pulley is slightly crowned so as to prevent the bell from flying off it. So this crowning of this pulley, basically it helps to keep the bell running centrally over the pulley, and this is one of the requirement in case of flat bell. Otherwise, if for high speed, if you as you increase the speed, so there is a high chance that if there is no crowning of the pulley, so this belt will either slip in this side or that side and fall off or run off that particular pulley. Okay, that is not desired. And as I have already said, okay, these P-bells, they are like having the first structure is kind of trapezoidal, and they are designed to operate in a V-shaped group. Okay, so this particular group on the pulley rim is made deeper, so that we can take the advantage of the wedge action. And because of that, as I have previously said, so these P-bells, they can transmit more power without undergoing any sleep compared to the felt. Okay, so the like this is one of the advantages. So other advantages of the P-belt over your flat belt, just go through it. Okay, so this much I hope that's clear. Let me know.
Yes, sir.
Okay.
Yes, sir.
Now
Yes, sir.
we know, suppose what is belt drive, why it is used, what are the advantages and all, what are the different belt material, what is the kind of belt types, etc. Okay, and how the velocity ratio is obtained, and what is the effect of sleep on velocity ratio. Those things also we have discussed. Now, as we have been already seeing, like there are different configuration for this connection of the belt. So let's consider the two basic configuration, that is the open belting and cross belting, okay, or open belt drive and cross belt drive. Now, this configuration, what we have been previously discussing, okay, having the one driver pulley and the driven pulley, over which we have got your belt on over it, suitable belt, okay, and there is a this slack side where basically the belt is leaving that particular this driver pulley, okay, and this is the tight side where it is something like the belt is being pulled on this part towards this particular pulley. That's why this is the tight side, that is the slack side, okay. And as you can see, when this driver pulley is rotating in this clockwise direction, belt is getting the motion like this due to the friction that is evident there in between the belt and the pulley material. And in this side, from the pull belt, actually that even pulley is getting the motion, and ultimately the shaft gets rotated. So in case of this belt, open belt type, what are the salient features? So here both the pulleys, that is the driver as well as driven pulley, they rotate in the same direction, and the shafts, okay, the shaft position is here. That is the center, basically shaft is there onto which to have suitable pulley mounted, okay, and the shafts are basically arranged in parallel. And generally, this for this particular building, the central distance, which is nothing but the center to center distance between the two subs, this particular distance, okay, this generally for open bell, it is 14 to 16 meter. That is the kind of range, okay. And if it goes beyond that, that is if the center distance is too large, what basically happens, the bell tend to vibrate in a particular direction, which is perpendicular to the direction of motion. And if this particular distance is too short, then the sleep in the belt, okay, in the belt type, it increases, okay. And because of that, as these two situations are there, or even for higher your central distance, as well as for slow, very low or short central distance, because of that, basically this type of open belting, okay, or open belt type, its use is kind of somewhat restricted for higher transfer of motion, okay. And this limitation of the sleep and transferring of motion, low power transfer, can be overcome by another building that is known as the cross build drive. Okay, so here what happens, as you can see, this is the driver pulley, this is the ribbon pulley. Okay, so this is the central distance between them. Okay, so now what happens in this case? So the connection between them is the belt is on the belt. Okay, so okay, so as they are kind of, they're as if they are crossing each other, okay, so that's why the name is cross filter. So here what happens, as you can see, the driver plays rotating in this particular direction. So from here the driven belt is going to get the motion, okay. Now from this side, this is the side of the belt, okay. So from here, once along with this particular belt, the driven pulley is going to get rotation in this direction. Now as you can see, the clockwise directional sense of rotation of driver pulley has been converted to anti-clockwise directional motion of this particular sub. Okay, so that means whenever you require this kind of your change in the directional sense, then also you can use this cross belt. Apart from that, for higher power transmission, also we go for this cross belt. So here, both the pulleys, they rotate in opposite direction, and the angle of contact of belt on both the pulleys basically is so from the center, okay, from the center to here, okay, ultimately, as you can see, the belt is not out over the whole circumference of this particular pulley, okay, but there is certain, at certain portion the belt leaves the particular pulley, and in this side at certain location the belt enters the pulley, okay. And from the center it makes a particular angle, and this angle of contact, it is the portion, okay, where basically the belt is in actual contact with the pulley, okay. So that subtended angle is basically known as the angle of wrap or angle of contact in case of that, okay. So now in case of your belt drive, first belt, right? Basically, this angle of contact of belt on both the pulleys are equal, and it can, if you compare it with the open belt drive, so it can definitely transmit more power compared to the open belt drive, as the angle of wrap here is more. Okay, So as in the previous case, if you see, okay, basically here the whale sleeps earlier. Okay, the contact is broken earlier. So and mostly in this particular case, if you look, okay, so up to this the contact was not made. So here itself the contact is broken. So that is another reason why a crossbell. And but in the case of crossbell, you can say up to this much. Here itself the contact is made. Okay, and up to this much the contact was there. Okay, so because of that, it can transmit more power. So, but one disadvantage that is there, as you can see here, this particular, even though belt drive is a kind of flexible drive and it can go, like it can some suitably, it can be bended, okay, it can it can be bended, okay, no problem is there. But because of that, as there is kind of belt has to bend into different planes here, it is bent here, okay. Similarly here also it is bent here. Okay, so as it has to be bent in two different planes, and in the meantime, it has got the relative motion between the belt and the pulley. So when the belt is continuously rotating over the particular pulley, friction also is there. So compared to your normal belt drive, okay, that is the open belt drive. Here we have got much wear and tear. Okay, so that is the open and cross belt drive. Understood? Yes. Let me know.
Yes, sir.
Okay. So next thing that we're going to discuss is, now I have been saying that this bell drive is kind of not a kind of policy drive because we have got sleep on there. Okay, and already we have discussed about the initial discussion about what happens if there is sleep. But now mathematically we will see what is the effect of sleep that is there on the velocity ratio, how to get that particular expression. So as we have previously said, so sleep we can consider it as to be the relative motion between the belt and the pulley. Okay, in actual sense, whatever be the motion in that particular pulley, we wanted to have the same motion transmitted to that particular belt. But due to sleep, there will be some relative motion. That means one is uh, getting, suppose the pulley is rotating, but the belt is not getting that particular motion. Then also there will be relative motion between them. So that is the kind of sleep. So the difference between the linear speed of pulley beam and the belt which is covering it, it's basically because of sleep only. Okay, and actually because of sleep, the driving pulley it cannot take the belt with it, and this is due to actually the insufficient friction between them. When your power transmission that is increases the frictional force friction, okay, then basically insufficient friction is there, okay, and because of that we can say that there is basically slip between the belt and the pulley, okay, because it cannot take the belt along with it, and it's kind of it is slipping over it. And because as I have previously also discussed, the velocity ratio of the drive it gets decreased, okay. So the slip it decreases the speed of the belt on the driving shaft, and it also decreases the speed of the driven shaft. How? Basically, if you look at the motion transfer from the pulley to the your belt as well as in the driven side, okay, from the drill to the pulley. So there are two stages involved. So slip it may be in either of the pulley and belt, suppose in the driven side, or maybe it may be only in the driving side, okay, or there may be sleep in both the sides, okay, both are possible because there are two stages involved. So yeah, wherever we the sleep, so this sleep decreases the speed of the belt on the driven shaft, and its effect is it also reduces the speed of the driven shaft. Okay, so now let's consider how to get that particular mathematically how to obtain the expression so as to see what is the how much is the effect of sleep that is there on the velocity ratio of that particular belt drive. Okay, so let's consider omega 1 and omega 2 be the two angular velocities of the driving and the driven pulley, and let's consider a slip in both the side, that is s1 is the percentage slip between the driving pulley and the belt, and s2 be the percentage slip between the driven pulley and the belt. Mind you, okay, generally the slip is given as a percentage, okay, percentage slip only, and let's consider the total slip is f, okay, that is the total percentage slip, and we'll be also considering the belt thickness. So let's consider the small t to be the thickness of the belt, and d1 and d2 be the diameter for the driving and the driven pulley respectively. So now what we can we already know this expression is equal to r omega, right? So similar expression for finding out the peripheral speed of the driving uh, your driving pulley, that is will be valid. Sorry. So we equal to omega, we already know. Okay. Now in the case of, if you consider the thickness of this particular wheel, then the your for the driving side is d1 is the diameter for the particular driving pulley. Okay. And also if we consider up to the thickness of the wheel, then the effective radius becomes d1 plus d by 2. Okay, considering the thickness, that is the r. And omega, it is nothing but, already we have considered omega 1. So peripheral speed of the driving pulley is omega 1 into d1 plus d divided by 2, considering the thickness. Otherwise it would have been only d1 by d2. Okay. Now we are saying that there is basically uh, a slip in the both the sides. Okay, that is this slip. Okay, now because of that particular slip, so speed of the belt on the driving pulley due to slip, how much it will be? Initially, if there is no slip, it would have been the same speed, okay, as that of the peripheral speed of the driving pulley. But there is slip. Because of slip, we know it gets decreased. Okay, and how much? We have already considered S1 to be the percentage slip between them. So what will happen? So this will remain same, omega 1 to d1 plus d by 2, and this is the effect of slip. So 1 minus S1 by 100. So S1 is the percentage slip. That's why S1 by 100 that we have to consider. And why we are eliminating why 1 minus this much? Because effect is to decrease the velocity ratio. Had it been increasing it, that it would have been 1 plus this much. Okay, but right now, this, because of this slip, okay, we are getting less amount of weight onto the weight. Okay, so this is the initial expected uh, speed. Okay, but due to slip, this must got reduced. Okay, now this same speed, this speed whatever we have obtained here, it is the same belt, right? So it is the same belt that is going towards the driven side, and from that side basically we're getting the motion will be now transferred from the belt to the driven. Okay, so now this particular speed whatever we have just obtained, it is the speed of the belt on the driven pulley also. Okay, so now from here what we can write? So peripheral speed of the driven pulley. Now once again we have said that there is once again in that particular side also slip is there, and S2 is the percentage slip here there. Okay. So now whatever is the belt speed, this much is the belt speed. Now from there will be another reduction, and the reduction is, we have said this remains like this. So 1 minus now S2 by 100, because S2 is the percentage slip in that particular side. Okay, this is from this expression. Also, in another way, we can directly write in terms of the angular velocity of that particular driven shaft, and considering the diameter of that particular pulley only. Okay, so just like v equal to r omega, using this expression, we can also write the same peripheral velocity speed of the driven pulley as omega 2 into, considering the thickness belt thickness d2 plus d divided by 2. So let's give this as 1, give this as number 2 expression, and both are basically same for the same velocity we are talking about. Okay, so we can equate them. Okay, so by equating and simplifying, what we can get, omega 2 by omega 1 equal to d1 plus d divided to d2 plus d with d 1 minus s1 plus s2 minus 0.01 s1 s2 divided by 100. And after simplify, this is basically this we have already considered s to be the total percentage slip. Okay, so this much value can write, we'll just replace it with s. Okay, and s is nothing but s1 plus s2 minus 0.01 s1 s2. Okay, so by considering the your ratio, okay, this is the effect of slip that is coming up here. So as you can see, had there been no slip, so the velocity ratio would have been omega 2 by omega 1 equal to d1 plus d divided by d2 plus d. But as there is slip, so this mass gets reduced. 1 minus s by 100 comes up. Okay, and this here, this s is the total percentage slip, not the individual slip, and it is given by s1 plus s2. It is not only just s1 plus s2, but s1 plus s2 minus 0.01 s1 s2, as can be seen while simplifying it. Okay, so that means what we can say from here. So velocity ratio you can write as omega 2 by omega, or maybe in terms of n, it will be n2 by n1. Okay, so here you can see it's getting reduced. Okay, that is the effect of sleep, is to reduce the velocity ratio. And where generally sleep occurs first? So sleep generally occurs first on the pulley with the smaller angle of flight. That is on the smaller pulley. After that, generally in the bigger pulley, sleep occurs. Yes, is that clear? Yes, am I audible?
Audible, sir.
Yes, sir.
Yes, sir.
Okay.
Yes.
Now, just like sleep, there is another phenomenon that is known as the creep of belt. Okay, so what is this creep? So once again, we will go back to the previous diagram where we show the like only we are considering the open belt fully. Okay, so here this is the like slack side tension in the slack side is T2. Okay, this tight side tension in the tight side we are considering T1. Okay, both the tension values are different. So this is the drive. It is different for it. Now what happens, as we know, the portion of the belt which is leaving the driven pulley and approaching the driver pulley is the tight side. Okay, this side. Okay, it is leaving this pulley and approaching the driver. So it is as if it is being pulled here. So this is the tight side. And the tension we are considering to be T1. And the part of the belt which is basically leaving here. So as you can see, the contact is broken here. Okay, so it is leaving the driver and it is approaching the follower. And it is the somewhat slack side, okay, having tension T2. So now because this particular difference between T1 and T2 is the actually the effective tension, and this effective tension is capable of doing certain work. Okay, so when this particular belt is moving over the driving pulley means from the tight side it is coming to the slack side. So that means previously it is in under tension, more tension, that is more T was more, now it is coming to the slack side, T is less. So the tension in the belt is decreasing. Okay, and if the tension decreases, so the belt length will somewhat contract. But on the other hand, when you consider the opposite side, that is it is passing from the slack side to the tight side. Now what happens, the tension in the belt increases, so it is under more tension. So what will happen to the length? So length of the belt, okay, gets increased. Okay, that means thus in the running of the completely that particular belt itself, in one side it is the belt gets contracted, another side it extends, and this happens continuously, continuous extension and contraction of the belt, it keeps on happening, and there is a particularly relative motion between the this belt and the belt, between the belt and the particular pulley, and this is known as the creep. Okay, so and because of creep there is somewhat loss in the power transmission due to it. And just like in the case of sleep, okay, this creep also reduces the velocity ratio. And how can there is an expression to get the velocity ratio, how to get it? So if you consider basically there is kind of elongation contraction that is coming up, and that means the strain is also there. Okay, so consideration of the modulus of elasticity of the bell material, and consideration of the strain that is on both the sides, that is the right side and the slack side, that has to be there. Okay, and like what is the strain, that relationship now will come up, and they will be affecting the velocity ratio. So how to get it? So velocity ratio is omega 2 by omega 1 or n2 by n1. Okay, so this is same after this must d1 by d2, it is same multiplied by 1 plus e2. Okay, epsilon 2 divided by 1 plus epsilon 1, where this epsilon 1 and epsilon 2, they are nothing but the strain on the tight and the slick side respectively. Or in terms of the modulus of velocity and stress, if you want to write, same thing can be written as e plus root sigma 2 divided by e plus root of sigma 1. So the sigma 2 and sigma 1, they are the stresses in the bell on the tight and the slack side. And as the bell material is the same uh, for the it is made of the same material, so E, that is the modulus of elasticity for the material, remains the same. Okay, so there will not be any E1 or E2, so it is the same E modulus of elasticity, because even though the belt is undergoing extension and contraction, it is the same belt material that is going under that. Okay, understood? Yes or no? Hello.
Yes, sir.
Yes.
Okay.
Yes.
Yes, sir.
Okay. Now, just like your gear, okay, so there is one law of belting also, just like law of gearing. So what does it state? It states that the center line of the bell, as it is using the pulley, must lie in a plane which is perpendicular to the axis of the pulley, or in a plane of the pulley. Otherwise, what will happen? The belt is going to run off the pulley. Okay, that is basically it gives you the indication about okay what should be the conditions so that the belt continuously runs on that particular pulley onto which it has mounted. Okay. Next, as I've been saying that basically suitable belt. Sometimes we are using this word, right? Okay, suitable belt of suitable length. Okay, so now we know that basically during the course of action, there is this kind of friction between the belt and the pulley that must be there, which is basically responsible for giving the proper drive. Okay, or motion transfer or power transfer, whatever you want to call it. So, if and generally during this course of work the belt is under tension. Okay, so now that means if that has to be there, that then if depending on whether it's a cross belting or open belting, a belt of suitable length has to be considered. Otherwise, if it is the belt is too lengthy, then definitely very easily without having any applying any tension and all, you'll be able to just under it over it. Maybe it will be very like hanging or that kind of thing it will happen. Or that if the belt length is too small, so depending on suppose if this is the central distance and these are the size of the particular two pulley that is there, depending on that, if the length is too small, then you will not be even like even will not be able to um, uh, like complete the particular belt drive. You will not be able to mount the belt over the two pulleys. Okay, so depends depending on like what is the central distance between the two sub, what is the size of the two pulleys and all, and what is the type of belting, whether it's a open belt or cross belting. So there is a suitable length of the belt that has to be considered. Okay, so now how to get that particular length of the belt which is required for open as well as cross belting. So this like expression I'm directly giving. So your task will be to just derive these two expressions. Okay, I have shown some of the parts. Okay, let's consider R1 and R2. They have this bigger pulley as well as this particular smaller pulley. Okay, and X with this particular central distance between them. Okay, and let's consider capital L be the total length of the belt which is required. And this 2 alpha is this particular angle which is subtended between the straight portion of the belt. Okay, so now if you extend it, that means the total angle is kind of 2 alpha. Okay, so that means and this is the angle of wrap, you can see theta. Okay, similarly here also you can see this much is the alpha. Okay, this is the okay, so now in that particular case of the drive, so how I can get, so L equal to I into R1 plus R2 plus 2x plus R1 minus R2 whole square divided by the central distance. Okay, and this angle of contact theta is generally considered on the smaller pulley in this only. And in case of your open bell drive, as you can see, so here this is 180 degree, half of it, that is 360, half of 360 degree. Up to this much, this is 180 degree. But as you can see, the wrapping is okay. The contact is made here, okay, and contact is broken here. Since this angle is theta and this is less than 180 degree, and how much less? So this is alpha. This much is alpha. So this much also is alpha. So it is the angle of wrap is 180 degree minus 2 alpha in case of your open bell drive. But in the case of cross bell drive, as you can see here, okay, so contact is made here and contact is broken here, and throughout this, okay, this is the theta. This is bigger than this 180 degree. This is 180 degree. Half of this 180 degree, and how much bigger? This is alpha, and this is alpha. That is 180 degree plus 2 alpha in case of your cross belting. Okay, so in case of cross belting, this 2 alpha is the angle between the belting. So here this is the 2 alpha. So you can see once again this is x. That is your central distance, and L becomes it is somewhat similar, but as you can see, this R1 minus R2 changes to R1 plus R2 here. Okay, so that is the only thing, and this is about the length of the bell. And similarly, as we know, power P equal to like power equal to F P that we know. So here the tension is also is a kind of force, and the effective tension is T1 minus T2. So this is equivalent tension, okay? T into V, that is kind of power equal to force into velocity, you know, okay? So this is the peripheral or the linear velocity of the belt only, that's small v, okay? This F, that is here the working forces, basically the tension, that is the effective tension, T1 minus T2. So power equal to T1 minus T2 into V. So that is empowering what? And T1 and T2, they are nothing but the tension of the tight and slack side of the belt in Newton, okay? And this v is nothing but the linear velocity of the belt in meter per second, given by pi dn by 60. Okay, d is the diameter of the pulley in meter, and it understood. Okay, similarly we have ratio of the driving tension, that is for the flat belt it is given by t1 by t2 equal to e to the power mu theta. So this expression will be recurred in while solving the problems, where mu is the coefficient of friction between the belt and pulley, and theta is in radians. Similarly, for V bolt or rope, this expression gets divided by sine of alpha, where 2 alpha is the groove angle. Similarly, we have got centrifugal tension. If you consider the centrifugal tension into consideration, okay, so then Tc is given by mv square, where the important thing is that this m is the mass of the belt per unit length, not only the mass in kg per meter. Okay, and the maximum tension which the belt can be subjected to, if you consider centrifugal tension, is T is this total tension in the tight side, because that is the highest tension, plus the centrifugal tension. Okay, and the maximum power transmitted by a belt. Okay, so for mathematical relation for maximum power transmission is the centrifugal tension has to be 1/3 of the tension. Okay, or Vmax in terms of velocity. So maximum velocity is root over t by 3. So these expressions was directly could be used. So in the next class, today we'll stop here. In the next class, we'll discuss some problems related to filtering. Okay. So any confusion in today's class? If no, we'll just take the attendance. So respond to your name calls. Milot Paul,
Present, sir.
Shankar,
Present, sir.
Arshisman,
Present, sir.
Rehan,
Present,
absent.
sir.
Okay, present. Partha.
Sir, present, sir.
Okay, present. Partha.
Sir,
Yes, Rehan present, present. Partha. Partha. Absent. Rishikesh.
Present, sir.
Permiki.
Present, sir.
Mahasol.
Present, sir.
Teza.
Present, sir.
Rishikesh Nath.
Yes, sir.
And Emil.
present, sir.
Okay, so thank you everyone for joining. We'll meet in the next class.
Thank you, sir.
Thank you, sir.